came to be. A black hole begins its life in the brilliant light of a dying star. Within the folds of our galaxy, the energy let loose by supernovae stirs the celestial mix. Shockwaves from these explosions cause gas to condense, then ignite. Stars are born, sometimes hundreds at a time. Intense stellar winds from these newborn stars sculpt majestic castles of gas, the great nebulae, long admired by astronomers. Yet, for the giant stars that set this process in motion, the consequences are grim. Back in the mid-1800s, mariners plied southern seas by the light of a brilliant star just off the plane of the galaxy in the constellation Carina. For over a decade, it was the second brightest star in the sky. Astronomers have been studying it intensively ever since. The star, named Eta Carinae, had undergone what's now known as the Great Eruption, an outburst that expelled two luminous lobes of gas that stretched some 12 trillion kilometers from end to end. Astronomers recently found that Eta Carinae is actually two giant stars closely orbiting one another. To explain the extreme turbulence of this scene, scientists modeled the fierce hot winds roaring out of these two companions. The orbital motions of the two stars allowed them to peg the larger one at 90 times the mass of the Sun. Eta Carinae is a supernova waiting to happen. In time, it will seize with convulsions, then collapse and explode. Throughout history, our understanding of space has been shaped by a handful of supernovae visible to the naked eye. Some archaeologists believe this drawing depicts a supernova spotted by North American stargazers in the year 1054. The same event was also recorded in China, Korea, and the Middle East. In Europe, supernova sightings help dispel the prevailing belief that the heavens are static and unchanging. The astronomer Tycho Brahe saw one in the year 1572. "I was led into such perplexity by the unbelievability of the thing," he wrote, "that I began to doubt the faith of my own eyes." In modern times, astronomers have intensively studied the remnants of the 1054 explosion, the famous Crab Nebula. Waves of radiation roaring out of the explosion have etched circular patterns in the surrounding gas, seen here in radio, infrared, optical, ultraviolet, and X-ray light. You can see signs of a jet shooting out of the central region. This energy is coming from a tiny spinning object in the center, the size of a city. This neutron star is not made of any elements, but subatomic particles packed by gravity into an ultra-dense sphere. Physicists think of it as a single huge atom. It's roughly equivalent to packing Mount Everest into a sugar cube. Yet some dying stars meet a fate that is stranger still. In 1796, Pierre Simon, the Marquis de Laplace, imagined a breed of dark stars so heavy their gravity prevented any light from escaping. This idea, a head-scratcher, fell out of favor for more than a century. Isaac Newton had described gravity as a force of attraction between two masses. Early in the 20th century, Albert Einstein's equations showed that gravity is actually the distortion of space-time by massive objects. Thus, a planet, or star, or even a galaxy creates a gravitational well that will bend the path of other objects, or even beams of light. Distortion of space-time by massive objects. As the physicist John Archibald Wheeler later put it, thus a planet, space-time tells matter how to move. Matter tells space-time how to curve. In 1919, the now famous Eddington expeditions set out to test this wild idea during a solar eclipse. Their data showed that the sun's gravity bent the path of starlight, just as Einstein had predicted. But also hiding in Einstein's equations was a very strange prospect that recalled Pierre Simon's speculation. If an object is dense enough, it will bend a beam of light back onto itself, causing that light to disappear. Physicist Karl Schwarzschild, director of the Astrophysical Observatory in Potsdam, Germany, took this idea to its logical conclusion. Working as an artillery lieutenant on the battlefront of World War I, he stole moments to pore over Einstein's new theory. As you see, he wrote to Einstein, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas. Schwarzschild realized that objects could become so dense, their mass would be packed into an infinitesimal point, a singularity. He calculated that these odd creations must be bounded by a larger spherical region beyond which no light can escape, the so-called event horizon. But how could such objects actually exist? In 1939, Einstein himself wrote a paper that sought to prove that these strange objects were impossible. But just a few months later, physicist J. Robert Oppenheimer and his graduate students published their own paper on the subject. Taking a fresh look at the mathematics of collapsing stars, they show that if the parent star is sufficiently massive, the force of the collapse will literally crush its core down to a point, an infinitely dense, infinitely curved speck of pure gravitational energy. Oppenheimer went off to spearhead the design of the atomic bomb, having laid the foundations of the modern science of black holes. The atomic age brought a whole new focus on the study of extreme physics. The bomb was terrifying proof, as Einstein conjectured, that a small amount of mass could convert to a huge amount of energy. Researchers studied the enormous forces released when atoms are split apart in chain reactions at the heart of atomic and thermonuclear bombs. Using advanced new computers developed to model and forecast these explosions, astrophysicists began probing the mechanisms at work deep inside stars, where lighter elements burn and fuse into heavier ones. They saw how this can eventually lead large stars to collapse and explode. This grim product of star death entered the popular imagination in 1967, when physicist John Wheeler called it a black hole. Astronomers were already at work looking for these monsters. In 1964, a sounding rocket recorded a high-energy X-ray source in the southern constellation of Cygnus. Later satellites recorded a pulsing rhythm in its light, punctuated by outlandish bursts of energy. After pinpointing its exact location, ground-based observatories detected a giant star that could not by itself emit X-rays. Astronomers deduced that Cygnus X1 is a star with an unseen companion, one that is eating it alive. Enveloped in a halo of glowing gas streaming in from the star, that partner weighs in at 15 times the mass of our Sun. The first confirmed black hole. This computer simulation shows how a black hole makes its presence known. Matter spiraling into the abyss forms what's called an accretion disk. The spinning motion generates powerful magnetic fields that whip up a hurricane of particles and propel them from the poles at nearly the speed of light. If you were to fall into a star-sized black hole, the pull of its gravity rises so sharply you'd be stretched out until just your atoms remained, what physicist Stephen Hawking once called spaghettification. Stellar evolution models suggest there could be as many as 1 billion black holes in our Milky Way alone. Yet, they are dwarfed by a far larger and far more powerful presence, lurking in the very core of the galaxy. The first hints of this presence came in 1932. The Bell Telephone Company was concerned about static interfering with what it saw as a revolutionary new technology: long-distance radio communications. The company tasked the radio astronomer Carl Jansky with finding the sources. Using this ungainly radio receiver, Jansky methodically scanned the airwaves. He traced most of the static to thunderstorms, some nearby and others far away. Then, on September 16, 1932, he picked up a rumble that he could not explain. This particular noise appeared when the antenna was pointed at the constellation Sagittarius, toward the center of the galaxy. It returned every 23 hours and 56 minutes, exactly one Earth day in relation to the stars. Word of Jansky's findings got out. He assured the public it was not aliens seeking contact. But it would take another 30 years for astronomers to find out what it was. In the 1960s, advanced radio telescopes began picking up signals from distant space. Not knowing just what they were, observers called them quasi-stellar radio sources, quasars for short. These bright bluish beacons emitted far greater energy than a star. What cosmic engine was driving them? Radio astronomers found that some featured brilliant extensions originating in the centers of galaxies and reaching millions of light years into space. Looking at their light spectra, researchers realized that these were actually jets of superhot gas speeding away at hundreds of thousands of kilometers each second. Could such a feature finally explain Jansky's findings?
Yes.
It would take a new generation of giant telescopes to reveal the answer.
Bedosia.
Just as the Hubble Space Telescope began its sensational run, several new observatories were christened on the mountains in Hawaii in the north and the Andes Mountains in the south. Two rival teams of astronomers, each zeroed in on the galactic center to see what was there. These teams each undertook a multi-decade effort to track a population of stars that seemed to orbit a concentrated source of energetic emission, called Sagittarius A star. Finally, in the spring of 2002, a star labeled S2 swooped in close, accelerating to a remarkable 18 million kilometers per hour. If its path near Sagittarius A star proved erratic, astronomers would know the galactic center was packed with multiple massive objects. Instead, its path was smooth. They concluded that S2 and its companions must be orbiting a single object, weighing several million times the mass of our sun. A supermassive black hole. This effort, more than 2.5 decades after it began, was recognized with the Nobel Prize in Physics. Since that discovery, astrophysicists have been feeding additional observation data into their supercomputers to better understand how clouds of gas flow around and into the monster, and how its immense gravity drives the motions of stars at the center of our galaxy. the star S2 will inevitably return to the black hole. The pull of gravity will cause its orbit to shrink, pulling it ever closer.